So now we're going to look at the part 2, the second lecture for chapter 18 in aromatic substitution reactions. And remember, what we just saw in the previous lecture was the mechanism that is in common for all of these electrophilic aromatic substitution reactions. And so we're going to look at just a couple more reactions that follow that same pattern. And then for monosubstitution, that's all we've looked at so far is monosubstitution. And then we'll start looking at disubstitution and multiple substitution reactions. In other words, putting multiple groups on the ring, multiple functionalities. And so we're in here, Friedel-Crafts acylation. That's going to be very similar to Friedel-Crafts alkylation. Then we'll look at activating groups and deactivating groups. So all of these groups that you've put on up here, these different substituents, can either activate the ring, the benzene ring, or deactivate the benzene ring toward additional substitution, putting that second substituent onto the ring. And that's what we're going to study now in this lecture. So, acylation, here's the acyl group, and alkylation, both form a new carbon-carbon bond. So, acylation reactions are catalyzed by aluminum trichloride as the Lewis acid, just as you saw for the Friedel-Crafts alkylation reaction. So this is going to be very similar. So here we have the acid chloride, carboxylic acid chloride. Once again, the chlorine has a pair of electrons that will be donated to aluminum. So the aluminum will bear a positive charge. Aluminum will bear a negative charge. Chlorine will bear a positive charge. So a pair of electrons in the carbon-chlorine bond will move on to chlorine, just as you saw before in the Friedel-Crafts alkylation, except now instead of creating just a simple carbocation, you have this carbon double bond oxygen. And so this is now called an acylium ion. And you still have aluminum tetrachloride as the counter ion. And so the acylium ion becomes the electrophilic reagent. Acylium ions are resonance stabilized. The pair of electrons on oxygen can move in and satisfy that positive charge. Now, oxygen is bearing the positive charge. Here's the mechanism. The acylium ion is the electrophile. So you have nucleophilic attack on carbon. A pair of electrons moves out onto oxygen, satisfying the positive charge. Now the positive charge is on a carbon in the ring. So that positive charge moves around the ring. This is the sigma complex, just as you saw before in all of the other electrophilic aromatic substitution mechanisms. Then the carbon that is attached to 4 other atoms bears the proton that is removed, and the pair of electrons in the CH bond moves back into the ring, satisfying the positive charge and restoring the aromaticity. And so now you have attached this acyl group. So this is Friedel-Crafts acylation. Notice CH has become replaced by this acyl group. And you remember that we were saying that there was an instance in which a primary alkyl group could not become attached to the ring. The primary alkyl group was rearranging to a secondary alkyl group. And so multiple products were being obtained in that Friedel-Crafts alkylation. So now you can see this acylation gives you the acyl group attached to the benzene ring. And this can be reduced. This can be replaced. This C double bond O can be replaced by CH2 using zinc and hydrochloric acid. And so now you can see that this is a great way to synthesize the product that has in it a primary alkyl group, and there's no rearrangement involved. So, and this actually gives higher yields than was observed in the other reaction that you saw in part in the first lecture for this chapter. And so we saw that polyalkylation was possible because the alkyl group activated the ring towards a second alkylation. But here you don't see polyacylation. You don't see further reactions because the acyl group is a deactivating group. Alkyl groups will activate the ring towards a second substitution. Acyl groups will deactivate the ring towards a second substitution. So you don't have to worry about that here. It's not a complication. So 10 different groups can be installed on a benzene ring using these reactions that you've seen. And so you saw bromination, chlorination, nitration, sulfonation, alkylation, and acylation. So these different reactions occur directly using just the electrophile. You will need to be able to know the reagents that give this particular substitution, and you will need to know the electrophile that these reagents provide. So you'll need to know the reagents, the substituents that is attached, and the electrophiles. That's 3 different pieces that you'll need to know. And here, using additional reactions, the nitro group can be reduced to an amino group. The alkyl group can be modified to be a tribromo alkyl group. The alkyl group can be reacted with a very strong oxidizing agent to give you the carboxylic acid in the substituent. And also the primary alkyl group can be obtained by using the acylation and then the reduction of the carbonyl. So this is a great review slide, and you can use this slide to help you ensure that you know all of these different reactions. Now, you've heard me talk about activating and deactivating. When you want to attach an additional functional group onto a benzene ring that is already bearing a functional group, you have to consider the characteristics of the functional group that's already attached. You note from what we've seen that these reagents are going to nitrate a benzene ring. But will it occur faster or slower because of this methyl group? And where will it go? There are 3 different places that the new the incoming nitro group, could become attached. And so you need to be able to predict those things. So toluene, we know that toluene reacts faster than benzene generally. Alkyl groups are activating towards electrophilic aromatic substitution, and that's because methyl groups donate electron density into the ring. And if the ring has more electron density, it is able to effect nucleophilic attack more easily. And so that's the reason for that. You have to be able to analyze these substituents. And so that's what we're going to do now. We need to look at the rate and the directing effects. Where does the alkyl group direct the incoming reagents? Which position in the ring? It will never go at this position bearing the substituent. It will never go there. By the way, you saw ortho, meta, para. This position is called ipso. And so the incoming group will never go at the ipso position. It will always go ortho, meta, or para. Okay, so I think I just finished discussing that. So what is observed when that reaction takes place is that nitro does indeed give ortho, meta, and para products. So you get some ortho-nitrotoluene, some meta-nitrotoluene, some para-nitrotoluene, but a very small amount of para. This is really typical. The main product is the ortho-nitrotoluene. So the alkyl group has directed the nitro group, the nitro functionality, predominantly to the ortho position, 63%, and 34% to the para position. So this methyl group, an alkyl group, this is typical of alkyl groups. The methyl group is said to be ortho-para directing because the incoming groups go to the ortho position and the para position. Compare the stabilities of the sigma complexes in order to see an explanation of why the group is directed to the ortho position through ortho attack or the para position through para attack. So if you look at what's happening, you can see attack at the nitrogen bearing the positive charge to give the cation, and these three resonance structures correspond to that cation. Here, if this pi bond attacks so that the bond is formed between the meta position carbon and the nitrogen, then this is the carbocation that is obtained. And you can see these three resonance structures. If the bond is formed between the carbon at the para position, the para carbon, and the nitrogen, so if the attack at nitrogen bearing the positive charge comes from the carbon at the para position, then this is the carbocation that's formed, and these are the three resonance structures. So this is ortho attack, meta attack, and para attack. So why are these, you see two of these are outlined in green. And so why are they outlined in green? Why are they highlighted? So you'll notice that here there's a positive charge at the carbon bearing methyl, and here there's a positive charge at the carbon bearing methyl. Now at the meta attack resonance structures, the positive charge is moved around the ring, but it is impossible to put the positive charge on the carbon bearing methyl. So what is significant about putting the positive charge at the carbon-bearing methyl? Well, alkyl groups are electron donating. And so here you have the positive charge attached, positive charge directly on the carbon that is attached to the alkyl groups. So here, the alkyl group donates electron density directly to the carbon bearing the positive charge. And here, the methyl group donates electron density directly to the carbon bearing the positive charge. And that is a stabilizing interaction. You don't have that possible in the meta attack. So it's possible when you have the product of ortho attack or para attack. And so these are very stable resonance structures. And that makes these two reactions more facile. So let's compare the energy diagram. So here is the ortho attack. You can see it's going through this structure, this carbocation. Only one of the resonance structures is shown. The other resonance structures are all still contributing, but this is the most stable one. And so notice that you've got the reactants leading up to, over the barrier and leading to the reactive intermediate. So this carbocation is at an energy minimum. And similarly over here, this carbocation is at an energy minimum. This is the reagents, the reactants. This is the transition state, and this is the carbocation energy level. And so this is at an energy minimum. So this is for para attack. Now notice meta attack, that was the one where the positive charge could not be put on the carbon bearing the methyl group. And so that very stable structure could not be obtained for meta attack. And so it is higher in energy. This reactive intermediate, the carbocation, is higher in energy. So the energy barrier leading to it is higher in energy. So it's harder to achieve this reaction that gives meta products, meta substitution. So the ortho and para products predominate. More of the ortho is obtained because you have two possible ortho positions. So you have 34% of the para product. This would be about, 31 or 32% here and 31 or 32% over here, because you have twice the likelihood. Okay, this is just a statistical effect. The methoxy group activates the ring even more because it stabilizes the carbocation even more. You can see that this is not the carbocation, this is just the reactant. This is just anisole that is bearing a methoxy group. And so you can see the pair of electrons on oxygen donates electron density into the ring. And so you can see this negative charge goes around the ring. The resonance structure is moving this negative charge around the ring. Oxygen is bearing a positive charge. So you have five different resonance structures, because here the double bonds in the molecule are rotating around the ring as well. So there's 5 different resonance structures that can be obtained just for anisole, the reactant. And so the anisole is very activated towards electrophilic aromatic substitution. the electrons in the benzene ring are very available. And so if you put anisole in the presence of bromine, you don't even need to use a catalyst. This will just react, with the bromine, and it will give you tribromination. So, so here's the polysubstitution that we were talking about earlier. These activators are generally orthopara directors, however. Okay, let me go back. Now let's look at when you have anisole as the reactant. So the pair of electrons moves out and attacks nitrogen bearing the positive charge. And so now the nitrogen is attached to the ortho position. In this sigma complex, it shows nitrogen being attached to the meta position. Here, the nitrogen is attached to the para position, just like you saw earlier. Once again, with meta attack, it is impossible to put the positive charge on the carbon bearing the functional group. And so this sigma complex is not stabilized by the methoxy group. However, if you can put the positive charge on the carbon bearing the functional group, then you have an additional resonance structure because the lone pair on oxygen can be donated into the ring and the positive charge can be moved out onto oxygen. And a similar situation here. The pair of electrons can be donated into the ring and the positive charge can be moved out onto oxygen. And so you can see why the methoxy group is stabilizing for the sigma complexes. And so it is ortho-para directing, and it also increases the rate of the reaction. So it's activating and ortho-para directing towards additional electrophilic aromatic substitution. So once again, what we're talking about here is bringing a second substituent in and attaching it to the ring. And if you have an ortho-para director, you will get mostly ortho and para substitution, and in almost all cases, the rate of the reaction is increased because of the additional electron density provided in the ring. It makes the reaction easier, so it goes faster. And here, this is the same thing that you saw before. So the sigma complex, the positive charge here, is stabilized due to the electron donation, due to lone pairs on oxygen. Same thing over here. And you cannot achieve that if you have meta attack because the positive charge cannot be moved to the carbon bearing methoxy. So it's exactly the same situation that you saw earlier. Now, that is a discussion that applies to all of the activating groups, electron donating groups, either through the sigma system like the alkyls or through the pi system like methoxy. Now we're going to discuss deactivating groups. So the nitro group is deactivating. So you can see that the carbon-nitrogen bond is polarized. Nitrogen is bearing a positive charge. And so electron density is going to be withdrawn through the carbon-nitrogen bond out of the ring onto nitrogen. And also, since the nitrogen is bearing a positive charge, electron density can be removed directly from the pi system by moving the pair of electrons involved in this carbon-carbon bond out here and moving a pair of electrons in the NO pi bond out so that oxygen is bearing a negative charge and a negative charge. And there's actually a positive charge in the ring. And so you might expect, since the ring now is bearing a positive charge, that it's going to be electron deficient and it's going to be harder to do an electrophilic attack on a ring that's bearing a positive charge. And indeed it is. So the rates of reactions where the benzene ring is bearing a nitro group are all slower. The rate of the reaction is reduced. And here are the different resonance structures. So this is electron withdrawing, so it's deactivating through the sigma system as well as through the pi system. So the nitro group is a strong deactivator. So nitrobenzene undergoes nitration 100,000 times slower than benzene. It's a strong deactivator. Okay? And the new nitro group comes in predominantly meta, 93%, only 6% ortho, and only 1% para. So you see the pattern. The groups that are activating are ortho, para, directing in all cases except one. The groups that are deactivating are meta-directing. Now, you'll need to remember that. Activating groups are ortho-para-directing. Deactivating groups are meta-directing. There's one exception, and that's the halogens, and we'll cover those in a minute. So it's convenient that this forms a very small number of groups. It makes it easier for you to remember this. So let's look at this. Here is nitrobenzene. There's a nitro group coming in. Nitrobenzene, nitrobenzene. The nitro group is coming in. This is ortho, meta, para. And so let's analyze this. So when the nitro groups comes into the ortho position, the positive charge can be moved directly onto the carbon-bearing nitro. Well, previously, that was stabilizing, but remember, the nitrogen in nitro is bearing a positive charge. So here you've got two positive charge on adjacent atoms. That is not a stabilizing situation. So this is destabilized, and the same thing down here. This is stabilized. This resonance structure is not stabilized. It's destabilized because you have two bonded atoms, each bearing positive charges. So this is why ortho and para are disfavored in this reaction. So meta is not disfavored because the carbon bearing the nitro group, remember nitrogen has a positive charge on it, the carbon bearing nitro will never bear that positive charge. And so here, this is not disfavored. It isn't that meta, the structures for meta attack, it isn't that they are particularly stabilized. It's just that they're not destabilized, and the others are. So here you have the ortho attack has a higher energy barrier because the carbon is bearing a positive charge, nitro is bearing a positive charge. Over here, carbon is bearing a positive charge, nitrogen is bearing a positive charge, and these are resonance structures for that intermediate. Now, for meta attack, you cannot move the positive charge onto the carbon that is bearing nitro. And so the meta attack is not disfavored. It's not favored or disfavored. It's that you see this predominate because the other two are disfavored. So that takes care of the remaining reactions and the activating and deactivating groups and the directing effects. There is just one remaining reaction that we need to consider, the activation or deactivation characteristics and the directing effects for it, and that is halogenation. And we will see that, we will discuss that in the next lecture.